Okay, welcome everybody, and thank you, Cyril, for the nice introduction. I will talk today about Möbius geometry processing. It's a line of work I did with my fellow colleagues, Christian Miller, he's an assistant professor in TU Vienna, there we met, and Ophir Weber from Bar-Ilan University. He's also an assistant professor, a colleague from my days in the Technion. So let us begin. So the primary motivation for what I'm going to talk today, even if it goes in a few other directions, is of course, like Cyril said, architectural geometry. And specifically, this is a little bit dark, the study of what I call like unconventional patterns in a way. Okay, you can see some examples from here. This is the Eye Museum in Amsterdam. It has a very specific pattern, a little bit dark here. The Museo Sumaya in Mexico City. The Blob in Eindhoven, also in the Netherlands. That's going to be a theme here. And the Epcot theme park in Florida. All of which are kind of unconventional geometric shape with unconventional patterns on them. Okay, so let's see what's mutual to these examples I specifically chose. Okay, what's the striking features? First of all, indeed, unconventional patterns, not just a triangle mesh, a quad mesh, or whatever that will be. And they exhibit a large sense of regularity as part of aesthetics, which means while the patterns are unconventional, they are kind of repetitive, symmetric, and so forth. So they're regular in a sense. And also, not attached from regularity, as I will see, they are mostly have, in geometry style, a very spherical and circular aesthetics. So that means that they are beautiful because they are very smooth and spherical. And even though they have curved parts, still the smoothness is kind of related to the sphericality. So those are the properties I would like to focus on today. Okay? So here are other examples of possible unconventional patterns, not only in architecture. It's a little bit dark here, that's the last time I complained about, but this is Roger Penrose on Penrose tiling. Okay, in essence. But there are things we even see in day by day, and we don't appreciate how much they are actually pretty sophisticated in terms of connectivity and pattern style. Of course, what also prompted me to do so is that where I'm located currently, Utrecht in the Netherlands, there is a very high tradition of unconventional patterns in Dutch culture. You see them everywhere, and mostly because they are must be derived from artists, local artists who worked with them a lot, about those symmetries, of spherical patterns, of unconventional ones. Okay, so first I will define what I'm talking about when I say unconventional. There's a lot of definition of what's a regular pattern or a semi-regular pattern, but I will make a little bit of taxonomy here. These patterns are what I call pure, because they are the only three tilings that have the same tile all over. The triangle, the quad, and the hexagon that tile the mesh regularly with all the symmetries you would like. Then there are the mixed patterns. Every face here is still perfect, but there is an assortment of them. And of course, still some kind of rotational transitional symmetry. So there are mixed patterns, mixed regular patterns, or Archimedean. And there are tilings that, well, they are sort of regular in some sense, but not in Euclidean geometry. So for instance, in a hyperbolic geometry, this tiling with seven sides and connectivity of 3 on the vertices, or spherical tilings. For instance, the most famous of which is the dodecahedron, that is made out of pentagons that do tile the sphere in this setting, but not the plane. Throughout this talk, I will talk about design paradigm, which is called geometry from combinatorics. That means you start from some mesh, basically, sometimes even just a flat pattern, and you just pick up vertices, drag them around, and then optimize for the rest of the vertices through some kind of measure, because you want the shape to be something of the sort. That's a very, let's call it commonplace way to create geometry in both design and architecture. Taking this pattern, you don't see here, but it's one of those 3-4-3-4. I will have a zoom in of this later on. Okay, putting some handles in space and optimizing for the smoothest pattern for the rest. Okay, so the only thing I got here is the combinatorics, and the geometry follows by the handles, and then I get this thing. All right, and if I can continue a little bit, for instance, I can keep interacting with it. I can keep putting handles on it, dragging them around. Here, I do this. Wait a little bit optimization. This is an important part of waiting here, but then it works. Okay, so I have another way to construct geometry. All right, so this was about what kind of objects I want to work with, what kind of design paradigm I have, but let's see what I want to achieve geometric-wise. So I need some kind of measure of how to achieve aesthetics with meshes. For this, I will refer to conformal equivalence, but first let's talk about what I mean. A transformation of anything is conformal if it's a local rotation and scale. Okay, what does it mean? That's a very dry definition, that also there's no shear. Okay, that means that if I have some mesh and I move some vertices around, I don't see the effects of those ellipses becoming very narrow ellipses. They keep their shape, they might scale up and down, like in the right image. Conformal transformations are considered as, well, good aesthetically because of this effect, they preserve features. Features look the same, they might scale up and down, but still it's very good in this sense. Okay? Also being used extensively in architecture. I think Mark Pauli talked about this probably 2 weeks ago. This specific work where they do some mesh, which is a conformal transformation of some auxetic material in the ground. And so both it has some kind of material properties and it preserves those hexagonal shapes. Okay, for instance, one already built example is the Creole pavilions in London, where it's still a curved shape, but you can see it's conformal to some very symmetric pattern in the plane. Which means bring to my next point. Okay, now I want to diverge a little and say, okay, fine. But I defined conformality as something, in a way, relative. That means something is conformal to something else, then it's good. But what's good in general? I just got some kind of pattern in the plane, and I want a mesh with my handles that I put in to be good. What's the best mesh for this pattern? Okay, so my answer is as regular as possible. So if I got some pattern in the plane, this quads and triangle, and I drag points around in space, I want the mesh in space to still keep the regularity of those elements. That's, for me, aesthetics. What does it mean and how does it relate to before? When I say it wants to keep its regularity in space, it means that it's in some way conformal to some original pattern. If there was an original pattern which was perfect in the plane, that if I do some conformal transformation for some surface, then it will be regular in my definition as well. Okay? Now, I say as possible because, well, there are meshes that are perfectly, let's call them regular. All those meshes, they are Archimedean solids, they are perfect, but even for quad meshes, there are two curious examples. One of them is like, if you take a perfect piece of quads like a paper and you just fold it around without stretching, all the elements are still perfect. So this is a regular mesh. But there's also what's called the polycubes. If you take meshes that are made of some kind of perfect cube, they are also perfect. Of course, there are all kinds of curiosities, like take Archimedean solids and glue them together. That's also perfect because all the elements are perfect. Okay? But those are very specific examples, and they are, let's call them theoretically correct, but not good enough for design. For design, we usually want as X as possible, so this as regular as possible. Okay, so for instance, I prescribe some constraints here, and I tell the rest of the mesh, please optimize for the faces and the one rings of the vertices to be as regular as possible. And that's what I get. Okay, for instance, notice the three curiosities I point here. First is this red thing. It's exactly the hyperbolic patterns you showed. I told every face, please be a perfect heptagon. That made it crease like a hyperbolic surface, because then it realized this curvature in space. The purple mesh, I told it please be as perfect as possible. Therefore, the quad things became a little bit like this piece of paper. So I got something like a mesh that looks like it's made of origami. But then this hexagonal mesh became a little bit like a geodesic dome for the same effect. All right, now let's see how I try to achieve it using regular tools in geometry processing. Usually in geometry processing, we use the paradigm of finite elements to do transformation, to capture them, to quantify them, and so forth. So that's the staple of geometry processing. That means we usually work with triangles where we put functions like deformation functions on vertices. So the function space, like the deformation space, is vertex space. We move vertices around. And then why do we want to know they are triangle? Because we consider the transformation to be piecewise-affine. So if you move all the vertices of the triangle, the resulting triangle that became out of the move is the deformation of all the other points in the mesh. It's kind of obvious to talk about this, but this is very important to understand why it's bad for what I'm trying to do. So it looks like this. If I take this quad and I move one vertex, for instance, the top left corner, this is how the rest of the vertices will move according to this assumption, that everything else blends linearly. So you already see a problem. This is highly non-conformal. We made a lot of shear in it. In fact, I made a shear by design. To be conformal in this definition, I have to preserve angles. And I cannot do that. Because if I take those two triangles and I preserve the angle of face F, I did nothing to it but rotate it and scale. And because one edge is already set in this, I have to do exactly the same rotation and scale to face G, and so forth for the entire mesh. That means that under the definition of piecewise affinity, there are no true conformal transformations that are not global similarities. Okay, that means it's not helpful to use this kind of paradigm. How do other works handle this? Well, they don't use true conformal. They use things that are as conformal as possible, or sometimes, and this is specifically in this work, Canonical 2011, they use things that are conformal in the continuous case, but discretize the equations. So you don't get the actual global similarities in the triangle meshes, but if you refine the triangle meshes a lot, you see this effect happening after effect, okay? But none of this will provide discrete conformality using FEM because it's not possible. Also, another problem, I kept talking about unconventional meshes. This is really not well defined for polygonal meshes. What's piecewise-affine on polygonal meshes? That's, if you actually try to do them piecewise linear, there's no way you could, there's no design space here at all. Of course, but there's even another problem. If I try to make regularity, that means basically I'm trying to make every triangle have the degrees of pi divided by 3, conformal to a regular quad mesh. So for quad mesh, I indeed get those funny developable surfaces, where if I try to make every quad have exactly pi divided by 2 degrees, I take some mesh, this regular mesh, and I make it as origami as possible. It dries out the mesh, except the singularity points, where it becomes like a cube, or the corner of a cube, or this case. However, if I try to do that for triangle meshes, this is what I get. It's still sort of developable, but it looks like crumpled paper. That means if I try to optimize for each triangle specifically, the effect is not good enough. So there's ways to handle this for specifically developable surfaces, but I will not get into them, some modern ways. That's not my point. I will diverge from this. Now I will offer a little bit alternative paradigms to look at transformations. So instead of piecewise-affine, I ditch this entire realm of thinking, and I'm starting thinking about surfaces as made out of circles. That means I don't look at them as triangle meshes or something like this. For me, they are circle patterns. Now, circle patterns come in several tastes. The one I'm going to be looking at is that every face is actually a triangle. Is actually a circle in which maybe there could be a triangle or something like this, but that's what I'm going to be looking at. Now, this is, of course, not something I invented. This has been around for a while. Not that much of a while, actually. I think about 20 years they started actually looking at this. The seminal works of Bobenko from Berlin, Suris, and so forth. That was their viewpoint usually for discrete differential geometry and specifically conformal stuff. To look at surfaces as made out of circles because they could say a lot of interesting stuff on them in that sense. Of course, there are several tastes of this thing. Nobody says that looking at surfaces from circles is specifically for one circumcircle per face. You can do a lot of things. You can have circumcircles pair like inscribed circles and look at them and their adjacency. You could have spheres pair vertex. Everything goes as long as this is the viewpoint you're working with. Okay, and then it's possible. Usually the research about it worked in two different directions that I'm putting here. One of them is to then, if you consider them being made of circles, you can start looking at about a lot of interesting things, Gauss maps and so forth, invent things like Christoffel duos, and have really, really nice theoretical properties, but a little bit of a limited design space. It was more like a mathematical thing. You could create dual surfaces, minimal surfaces, and so forth, but not always control the boundary as you wished. Another approach is this Young et al. And also those things is just to optimize for these properties. Okay, so do you have, I want one circumcircle per face, so then I'm saying something like, okay, I'm optimizing for this as a constraint. Sum of angles equal pi in quad meshes, for instance. But those are hard constraints to optimize for. And when you just optimize for something to be in circular, it's not always that you get what you bargained for in this sense. So when I began, I sought after some kind of another design space which has some kind of guarantees to do things. So first of all, how the transformation goes. This is our faces F and G. Now I don't consider everything that happens inside F and G. I don't see the triangles. I see two circles, and I'm talking about this, how this red circle goes to the other red circle, and the blue circle goes to the other blue circle. If I want the underlying triangle mesh, well, I just take it from the adjacency relation. I have an edge here, which is exactly the intersection point of those two circles, and so forth. And then I ask myself, okay, you started with conformal, you wanted this because you want conformal transformation. What is conformal in this sense? So the natural, we looked at piecewise-affine, linear transformation for triangle meshes. That's the perfect space to look at when you're looking at simplices. Now I'm looking at circles and sphere. So the perfect geometry to work with is the one that preserves them, aka Möbius geometry. So let me give a little bit of a crash slide for this, okay, what Möbius transformations are. Möbius transformations are transformations that take spheres of any dimension and spheres to other spheres. But spheres also means here planes. Planes are like spheres here with the center at infinity radius. It looks like something you never met before, but this is actually something you see a lot. For instance, the most reasonable example that you can try at home is stereoscopic projection. You take some kind of sphere, which is kind of hollow, you put light above the north pole of the sphere, and then you can see on the plane exactly the Möbius transformation of it to the plane. Okay, and you can play with it. There is even a nice video I can send you if you are interested. Why Möbius transformation? Because they comprise similarities. Möbius transformation also include everything that is just a rotation and scale. And the curious inversions in sphere. That means it's kind of, you take some kind of sphere, there's some object, and you reflect it in the sphere, like a lens, in a way. That's sort of what happens in this stereographic projection. And they are conformal. Conformal means they are locally described by change in scale and rotation alone. In fact, not only they are conformal, they are the staple of conformalness. For instance, in dimensions bigger than 2, yes, which I kept showing here, they are the only conformal transformations. There's no others. So you cannot do anything else. Now, except at poles. Möbius transformations have poles. You can even see the pole here in this example. You can see I made this square into some part of a circle. But if I look at what happened to the center, yeah, you can continue the lines and see that the lines that used to be parallel here meeting at infinity now meet at a finite place. That's a pole, if I take it backwards, the other way around. Okay? Or in the stereoscopic projection, we have the north pole. That's the pole of this projection. All right. Now I will delve a little bit more into what I do because I work with Möbius transformation in 3D, and they require quaternions, okay, which is a whole different mess of their own. So let me also try to give a little bit of background to it. What are quaternionic transformations in general? So quaternions are essentially, well, vectors in R4. Okay, they are 4 numbers, but not just any 4 numbers. They have a specific non-commutative algebra between them, so operations. And a little bit less specifically, those 4 numbers divide into 2 parts. One of them is, let's call it the vector part, the x, y, z. The last 3 numbers, they are the imaginary part of the quaternion. And the first one is the real part. In computer, they are being used in mathematics, but mostly you see them a lot in computer graphics. They are used to describe rotations, so forth, in robotics a lot. They're used to parameterize things moving in space, in mechanics. And we identify vectors in R3 as having 0 real part. So they are imaginary quaternions. So if I want to do Möbius transformation from R3 to R3, I have to use a transformation that is imaginary preserving. That means it only takes vectors with 0 part and to other vectors in 0 part. Generally, usually, we talk about transformation that just keep the real part intact, don't change it. That's what, if this happens, it usually happens as well if they're continuous. Now, when I talk about a quaternion, I will refer to, let's call it a polar decomposition of a quaternion. With 3 parts, 3 of them are very important. The first is the size of the quaternion, the absolute value, which is basically the norm of this vector. We also call it the modulus. It's a name that's not very well known, usually used for complex number, but it means the same. It's just the absolute part. Then there is the phase of the quaternion. Every unit quaternion, that means after I divided away the modulus, can be done in the following form. There's a cosine of some phi, and then there's the imaginary part, which is just times this sinus phi. And this phi is the phase of the quaternions. For those of you who know computer graphics, if you rotate stuff with quaternions, that's actually the rotation angle that you're going to be using. Well, half of it, mostly. And then there is the last part, which is the unit direction. So this unit vector v. Good. So now I still need to define what's a conformal transformation. The fact that I'm using circle did not do much. It's just a paradigm. Is every transformation between 2 triangle meshes is a transformation between circles. I need to do something extra. So I'm going to be using this. Now, another shift of paradigms here is not to define conformal by the transformation that does something. It's actually define transformation by what it doesn't do, the invariants. So that means if a transformation doesn't touch something, then I consider it to be conformal. There's a conformal invariant. For instance, in the continuum, the angles between every 2 lines are conformal invariant. They don't change. Although it rotates, moves around in space. But you can say, if I say preserving angle, that means angles are an invariant. But they are not anymore for me, so I need a new one. So the one I'm going to be using is the cross ratio. It's actually very simply defined. Now I will do it first in the complex plane. You take those vertices as complex number. Zi of j is the edge, zj minus zi. And then you multiply and divide them together and get some mysterious size called the cross ratio of this object. Why do we use it as is? Because if z goes under a single Möbius transformation to w here, well, omega, the cross ratio is preserved. Not only that it happens, it's an identity. Like it means Möbius transformation. If you have 2 sets of 4 points, and you have the same cross ratio, there is a Möbius transformation between them by design. So that cross ratios are actually an equivalence class of Möbius transformations. They refine the space. That's why it's defined this way. All right, that's very nice, but that's in the complex plane. So I eased it up. What happens in 3D? Okay. Well, very much the same in a way. I define the cross ratio in 3D very similarly. Instead of complex numbers, I have imaginary quaternions. I'm getting a cross ratio. The cross ratio looks very similar, if you recall, just that I have to keep the same order because quaternion multiplication is not commutative. You could use another order, and that has the same power of expression, but you need to be consistent everywhere. So that's a nice choice. Now, what happens to the cross ratio if I do a quaternionic Möbius transformation? Okay, which means I express in quaternions similarity, inversions of sphere. I deliberately don't want to give the specific equation for it because It's actually not helpful to understand what's going on. Okay? What happens is the cross ratio gets preserved almost. It's conjugated. There's mean I'm getting that the new cross ratio is like the old cross ratio, except multiplied from the left by some size. Never mind the C and the D, yes, it's the coefficients of the Mobius transformation, and by another number in its inverse, which, if you know computer graphics, means a rotation. So that means that the old cross ratio, I keep the modulus, it has the same modulus, the same phase, so basically like the complex number that results from the quaternion, but it does rotate the unit vector. Now, how does it rotate the unit vector? What happened to it? I will talk about it a little bit later. So instead of piecewise linear, the paradigm I'm going to be working with is piecewise Möbius. That means basically I define a transformation as giving a single Möbius transformation per phase, where I'm telling it to, if you do some transformation to F and some transformation to G, then those transformations have to put those 2 points in the same place in the target. That's my condition when I do this. Okay? Then I'm calling it piecewise Möbius. And I measure conformality by how much a cross ratio change. So, for instance, this is in a complex plane, but it doesn't matter. If I do this one transformation per F and one transformation per G, I look at the cross ratio that change, and it tells me how much I am changed conformally. It also works for non-polygonal meshes, of course, because I'm just saying I have a quad mesh, I transform this quad mesh. Okay? Let's see how much is cross ratio changed specifically. So it doesn't matter that it used to be a triangle or not. But I didn't win the system, because both in 3D, it's a little bit complicated, I won't get into it, but in 2D, setting those 3 points in a single transformation is already enough. Yeah? In 2D, one transformation is determined by those 3 points. In 3D, there is a single degree of freedom, which is how to put the sphere on it, but I won't get into it. Okay? If you want, we can talk about it later. So that means that I still have this problem I had in conformal transformation. If I use a Mobius transformation to this, and then the same one to this to preserve the cross ratio exactly, because I want like perfect conformality, that means it will happen to face H, I, J, K, and so forth. And that means I need a single Mobius transformation to the entire mesh, and it's still not interesting design-wise. So I need a weaker version of preserving things. I cannot preserve the actual cross ratio. I need to weaken it a little bit. So I have 2 terms of discrete conformality, in which instead of preserving the cross ratio, I preserve either only the modulus. That means that I have 2 transformations that move the mesh around, but only preserve the norm of the cross ratio. Another interpretation of this, by the way, is to have a single scalar number per vertex and scale the edges accordingly, the lengths of the edges. That's what happens. And if you know a little bit of literature here, that's been called discrete conformal transformations by Springmore and all. That's a very commonplace definition of discrete conformality. So one can describe this by this piecewise Mobius transformation that keep the absolute value of the cross ratio. That's exactly the same. Instead, I can opt to keep only the phase of the cross ratio. So that means I allow the Mobius transformation to transform, but the phase stays the same. Now, why the phase? What's the meaning of the phase? As it happens to be, the phase of the cross ratio has a very specific meaning. It is the intersection angle between those circles. So I do a Mobius transformation to one circle and to another circle, and the difference in the cross ratio will tell me the difference in the intersection angle. It's actually pi minus, it depends on how you define those kind of intersection angle exactly, but it doesn't matter. Okay? Now this has been called also discrete conformal in the past. The problem is this is not a definition of conformality, it's extrinsic. It doesn't involve only the metric, so it cannot be conformal by definition. Conformal does intrinsic stuff, so if you have an isometry, it's supposed to stay the same, and this doesn't. It depends on the dihedral angle also. So this is only conformal in the plane, but it's still a measure. We call it intersection angle preserving. It's actually a discrete Willmore energy, but I will describe it a little bit later. I cannot have both at the same time. Having both means that I preserve both the modulus and the phase. That means conjugation. And that's exactly a single Möbius transformation. So those are exactly complementary weakening of the single Möbius paradigm. I can either do only this or none of them, of course, but that's every transformation, but not both. So that's a nice like taxonomy of the space of possibilities. Okay? Right. So I will talk a little bit about optimization later. That's only summarizing this part. Basically, the optimization term is I put some vertex constraints, I use them, and then I optimize for the cross ratio of the new mesh to look like the old one up to something, like preserve the modulus, preserve the intersection angle, and so forth. Right? Just in complex, I use complex numbers for 2D and free quaternions for 3D. And since I allow to give a single Möbius transformation per face, it doesn't matter to me that if they are, if they used to be polygonal or such, except that if the original face was circular, then I do get another circular mesh. This transformation is circularity preserving because it's a Möbius one. Let me show one example of this. I didn't give details of optimization. I will give later in another context in a few minutes. So this is an originally circular mesh. The colors you see is difference from circularity. That means every face is actually two circles, and I saw the intersection angle between them. If it's 0, it's a single circle. Okay, so it's blue. So now I move vertices around, optimize for the rest to be preserving the cross ratio as much as possible. And you see the colors stay the same. I'm not cheating here. It does compute them all the time. Yes, and the mesh keeps its circularity, relative circularity. So you see the transformation is pretty much conformal as we perceive them. Yes, even if it's a really, really big transformation. So this works nicely even for quite coarse meshes. Yes, let me move on. Okay. So this was specifically about conformal transformation, but I talked a lot about regularity, aka conformal to something regular. And then I want to have a little bit of a different but the same viewpoint on it, in which I will also talk about our modern way to optimize this. Okay? So I define a mesh to be regular, Möbius regular, if every face and every one ring are regular, Euclideanly regular, so it means totally symmetric, everything you would think about regularity, up to a Möbius transformation. So that means a Möbius transformation of something that used to be regular in the plane. If you take the regular triangle grid and do a Möbius transformation, that's what you get. For me, this is still regular. So I allow conformality in the mix. Okay? Or this mesh that is just some kind of circle pattern, which I took the Möbius transformation of. So those are perfectly regular in my terms. And those are almost perfectly regular. That means that I took some mesh, moved some points around, and optimized for the rest to be as regular as possible, which means they are conformal to some perfect existing or not existing, as I will talk about, regular pattern. All right. Now, to give a little bit of names, what is this perfect pattern? I call it the canonical embedding. Okay, that means that all the rings that are Möbius transformation of this creature are for me regular. It's some kind of equivalence class. This and all its Möbius transformations. It's not some kind, it's exactly an equivalence class. So with this, I take some kind of mesh. That's the mesh you've seen in the video before. Okay, you see it has 4s and 3s, and those are perfect patterns. I prescribed some positional constraints. I'm saying the vertices that used to sit here now have to sit there. Somewhere up. And then I optimize for the rest of them to be conformal to the original ones. Okay, or as regular as possible. Yeah, and it looks like this. You will notice already something peculiar. I didn't optimize for any actual geometry. I didn't say, please be smooth. I only said, please every vertex and every face be the Möbius transformation of some perfect face and vertex, and still it looks very spherical. Okay, so there's a sort of side effect here, but it's not a side effect, it's by design. First of all, That's very fine, but the problem is that there are no regular meshes, okay, except a very specific class of things, or in the plane. If you look at this example, it cannot be made regular. It's imperfect. We have nodes of 5 and nodes of 6. You cannot connect them together such that each one ring will be the Mobius transformation of a perfect one ring. There's a clash in angles. Of course, you could refine it and make the error be a little bit more about the singularity, but it will not go away, in essence. So how to do as Mobius regular as possible, that's also a problem, but it's even worse. I mean, if you think about it, the ring of 5s can have a canonical embedding where you put perfect triangles, and the ring of 6 is, of course, the regular triangle mesh. So individually, they can be perfect, not together. But not all rings are like this. If I have degree 7, yes, there is no perfect embedding. There's no way to put triangles in Euclidean geometry in a setup where they are all perfect. Okay? You could maybe in other degrees, but it's also going to look terrible. So we need to expand the definition of what we consider as regular. For instance, I'm saying if I have degree 7, for me this is the new regular. If I put them in a perfect heptagon. So those are not regular triangles, but for me, if a ring is a Mobius transformation of this is perfect. Okay? We call this process canonicalization, making something that is not canonical to canonical. The reason why we use a very weird word and not canonization is because canonization is the term in the Catholic Church to introduce saints. So we don't want to reuse a term that has much more important sense. So we invented another word for it. Reviewers, of course, complained, but we explained, so it worked. Now let's see what does happen. I'm doing here a thought experiment. I'm taking some mesh. I'm telling every ring and every face, please be the Mobius equivalent of a perfect ring, as much as possible. So all the rings compete with each other in a way. I didn't tell you how to do this yet, but that's less important than the result still. Okay? Something peculiar happened. I took this bunny. It was very irregular quads. I told every vertex and every face, please be regular as possible. I got a sphere. Yes. You see also that the sphere looks nicely like some kind of constellation. Everything is very symmetric and sort of. Okay, interesting. I did it to another mesh with a totally different connectivity. It still got a sphere. Now, if I do it to something really, really highly irregular, but with a degree 1, I'm getting a Dupin cyclid, which is the Mobius transformation of a torus. Well, it's discrete, so it's not exactly a Dupin cyclid, but something that looks like a Dupin cyclid. Okay? It's not a chance. That's just the way Mobius regularity is built. If I have to be a little bit spoil with the idea ahead, I was talking about things that are the Mobius transformation of something regular. Things that are regular are defined by something perfect in the plane, usually. If this is a Mobius transformation of them, you would expect something spherical. Okay, that's like the intuitive explanation of it. Why it becomes like a Dupin cyclid, which is a little bit too good to be true, I don't know. But we'll talk about what happens in spheres specifically. Okay? So first of all, my conventions are as follow. This is something I call the triangle. I won't use all of them, but just in case. This is something I call a triangle flap, 2 triangles. This is a one ring, okay, central circle and all its faces. And specifically, the red part of the one ring is something I call the vertex star. That means I only cut away the triangles around it. So the emanating edges from the central vertex and their connections. I won't necessarily be using it, but just in case I say those words. Now, everything about regularity, and in fact, everything I talked about conformality from before, can be attributed to this creature I'm going to be talking about, and that's the corner tangent. So, if I look at the vertex star, for instance, and I look at one triangle, and I look at the circle around it, and it's touching at the central vertex I, and I take the tangent to the circle. It's a single line. There's always this line. This line is the corner tangent. It's something that I touch. And for the one ring, I can collect all those lines. Specifically, I don't collect just a line. It's a specific edge, let's call it. So it's sitting on this line that has this formula. I will explain a little bit later why this formula exactly. But this very oddly simple formula gives you this tangent at I. So if I have a ring of degree D, I have D of those. Why do I use this specifically? Because the cross ratio of those 4 points, I, J, K, L, is the next T divided by the previous T, okay, in quaternions. You already see a pattern here. When you do in quaternion something divided by other, that means one is rotated to the other by some vector which is normal to both. That's how quaternions work. So the cross ratio is actually the vector that rotates a T to the next T. Okay? So you already see some kind of pattern forming here in the geometry, but I will make it a bit even clearer. Now those are not just segments all around, they actually form up to a polygon. So if I look at this definition, the way I defined it, qij minus 1 plus something minus 1, and then it appears again in a minus in the other. If I add them up, they close. So the sum of those edges is 0. That means they are actually a polygon, some abstract polygon of edges that looks like this. So I collect all those tangents and add them. Okay, who cares? Well, why did I make this construction? It's nice because it's leading somewhere. This thing is going to tell us everything we need to know about conformality. First of all, I already know that the cross ratios are normal to all those corners of this polygon. So it's a polygon where the cross ratio is this normal space. Okay? And now the big deal here is that if I do a Mobius transformation of this ring, what happened to the tangent polygon? It transforms like a similarity. That's perhaps not entirely surprising. I told you that under a Mobius transformation, the cross ratios transform also like a similarity. They are conjugated. So if I do a single Mobius transformation of this ring, the green to the green, all the cross ratios just rotate, and the tangent polygon rotates with them as an entity. Okay, that's not entirely surprising. All right, fine. So for instance, I would now say in conformal transformations, how do I want conformal transformation? I just try to preserve the lengths of the tangent polygon, the angles between it, and so forth. Of course, by the way, the angles in the tangent polygon are the intersection angles, because they are rotated by the cross ratio. Okay? So let's see what special structure does it have. In the context of a Mobius regularity, if I'm saying that something is Mobius regular if it's a Mobius transformation of something perfect, that means that I can see if something is Mobius regular without finding this Mobius transformation. I look at a ring, I look at the tangent polygon I just constructed. If it's regular, yes, I have this property. I don't need the Mobius transformation itself. This is my invariant. If the tangent polygon is perfectly regular, I am Mobius regular. So what I need to do is to optimize for the regularity, the Euclidean regularity of the tangent polygon. I reduced my problem. This is another way to say that in a perfect regular ring, which is also uniform, everything is triangles, it's perfectly Mobius regular if all the cross ratios are equal. I have one cross ratio that fits all the vertices around it. That's the same, okay? Of course, if it's 1, because it's a regular ring of degree n, then all the intersection angles are just the angles of a regular polygon, okay? But that is a little bit non-consequential at the moment. I don't want to talk about this a lot, but I have a very similar definition for mixed rings. It just depends on the degree of the face. So if you want to make a Mobius perfect, the angles will scale with the degree. There's a formula for this, but it's not that important. The only thing that's nice to say about this is that you will get a circular tangent polygon. I mean, it's not regular, but it's still concyclic, which, by the way, apparently proves some kind of theorem on the intersection between a sphere and the polyhedron. My colleague Christian knew about it, but I didn't know about it before. It's kind of an alternative proof for it, but fine. I think it's actually written in our paper, so. All right. Now, how do I optimize for this? Then Mobius regularity. I just do what I said. That means if I want to optimize for Euclidean regularity, so a polygon is perfectly Euclidean regular, I just say every consequent two edges everywhere in the mesh have a rotation between them, like a normal rotation between them, which is the same on the face. So that means symmetric and regular. If I want Möbius regularity, I need to do the same with the cross ratio. So I'm saying I want all the cross ratios around a one ring to be the same. Or if the one ring is mixed, then not the same, but something that depends only on the degree, which is constant. Okay, but my definition of perfect. Okay, so that's on every face, and that's on every one ring. Now, those of you who know about optimization will immediately see this looks horrible. Okay, I have expression here with a minus times itself, degree 8 polynomial. It looks terrible. Except it's not actually so terrible. In all my experiment, this worked really nice. My explanation, which is not really a mathematical explanation, is because this is really bounded. It's not like you could scale the mesh and you will get a better energy, because this is a cross ratio. It's invariant to scaling. So if you put boundary conditions and you optimize for this, the energy will anyhow be bounded. It cannot explode. To make the energy explode, then you need to distort the cross ratio much, and it's like the opposite of what you're trying to optimize for. So like, let's call it my experience with it is that this is a very stable energy, although it's very nonlinear. But I don't have any theoretical analysis of this, and I think it's hard to do anyhow. It's just like this. For total energy, I use a mix between Möbius regularity and just Euclidean regularity. Now you would say, hold on, you wanted something Möbius regular, why are you contaminating it with some actual Euclidean regularity? Well, the answer here is that Möbius regularity is not well defined because it's up to Möbius transformation. That means if I take a mesh and I do a Möbius transformation of it, and it can be a continuous Möbius transformation, so just a deformation, I get the same energy. For optimization-wise, it's not good. It means I have several solutions of the same energy. Yes, who of them is better? Then I use the other expression, which is kind of small magnitude, usually 0.01 versus 1, just to say, okay, but I prefer something that is Möbius regular, but from the Möbius regular meshes, the ones that it still keeps the scale a little bit down, does not go crazy with the conformality. But I can also play with it. I can get something really round versus something really like dry and developable with this playing of this parameter. How do I optimize for it? Nothing special. Okay, it's just Levenberg-Marquardt on this nonlinear least squares. It's kind of terrible speed-wise. Okay, you have to wait a lot, and that brings me to my actually next point. A little bit next point. First, I will show some examples. Okay, in all of this, I constrain the boundary of some mesh and optimize for Möbius regularity of the rest. So you see, it has this kind of very spherical, nice behavior, and the meshes look great. Here I put some positional constraint and optimize for the rest, so it has still kept this nice conformal appearance. In this case, I just put a little bit of conformal stuff and optimize for it. It became like a blob toy because it's as spherical as possible. Now I want to complete a little bit here because some people here are more mathematical savvy. I talked about preserving the phase. I talked about preserving the modulus. What happens with the vector part? I didn't talk about it at all. Things were conjugated, so that means the vector part rotated around, but what is it? Well, what exactly did I get for it? So it's not just something. It has a very specific meaning. So again, I have the modulus, which I preserved if I want conformality. I have the phase that I preserved if I want intersection angle. What happens to this? Well, if you have 4 vertices, the cross ratio at the vertex where you began with, the vector is the direction of the circumscribing sphere. So 4 vertices in space define a sphere. The sphere, by the way, can be the plane, yes? And then this vector is in the direction that goes between the center and the vertex, like this. So if you take the cross ratio, by the way, from the other point around, those are 2 lines that meet at the same point, and that's the center of the circle. If it's planar, they meet at infinity, yes, projective-wise. Okay, nice, yeah, but this actually, I already talked about this thing just in another way, okay? If you recall, yes, I said that if I want to make something Möbius regular, I'm trying to make all the cross ratios the same, right? Making them all the same means they all turn in the same direction. That means that there's a mutual sphere on which the entire one ring sits, because all the cross ratios point in the same direction. That's why you got spheres. But let's make it a little bit more concrete. So, if for every 4 points, the cross ratio points in the direction of the mutual sphere, then if all the cross ratios around the one ring point in the same direction, no matter if they're equal, just if the vector part points in the same direction, then the entire one ring is on a sphere. Or in other words, the tangent polygon is planar. That means all its normals are pointing in the same direction. That's actually not the first time it appears before, but in a totally different context. There's this, I don't think I actually wrote the site and I have to write it down. Bobenko and Schroeder paper from 2005, they talked about discrete Willmore energy. They actually said exactly that, but in other words. They said, by the way, Willmore energy is the energy of being as much spherical as possible. So a one ring is perfectly discrete Willmore energy 0 if it's all the vertices are on a sphere. Okay? Which means planar tangent polygon in my setting. So what they said in their paper, they said, well, discrete Willmore energy is I'm looking at the intersection angles of this one ring. If they sum up to the sum of angles in the flat the polygon, then it's discrete Willmore energy 0. But it's saying exactly the same. So if the angles sum up, they are perfectly planar, except they made a distinction between two cases. One of them they call the inscribable case. That means also that the tangent polygon is convex. So they have convex angles adding up. But they said, well, there are cases that are only inscribable if you allow the angles to be this way. So it's not convex. So this kind of combinatorics can only be inscribed in a sphere, discrete Willmore energy 0, if you allow for non-convex tangent space. Which brings me to another point. Discrete Willmore energy is not much. Willmore energy, the continuous one, is usually a measure of niceness from shells. It means spherical, but also locally spherical. So you're like a constant mean curvature surface or something of the sort. In this case, discrete Willmore energy means all vertices on the sphere, aka take mesh, normalize coordinates, you got discrete Willmore energy, even if it's a mess. So being convex is already some measure of niceness, but Mobius regularity is another one. Mobius regularity says, I don't only want it to be convex, I want it to be as regular as possible, which is convex and trying to be planar. However, that means trying to be planar. So if I'm trying to optimize for planarity, for regularity, if I am able to be perfect, then I'm also planar. But I cannot always aim to be perfect, and therefore I'm not always a planar. So if I'm trying to optimize for regularity, I might miss planarity if I have other boundary conditions. Let's look at this example. This is perfect, Mobius regular, perfect to Willmore. It's on the plane. This as well. But then I took the boundary condition and sheared them. It's still discrete Willmore energy 0. Yeah, because it's in the plane. It's not Mobius regular because it's sheared. So if I'm trying to constrain the vertices to lie in the same place, so for instance, only the other layers, and trying to optimize for Mobius regularity, it will start blobbing, doing this wave behavior. Because Mobius regularity is trying to be stronger. Okay, here's some example of this working unconventional patterns, like you have zoom-ins. For instance, if you take a Penrose pattern, for some odd reason, it still behaves with a very spherical behavior. Although I don't have any explanation to this. It's not generally have to supposed to behave this way. Maybe it did because of this Willmore energy thing. Okay, or if I use this kind of Catmull-Clark pattern, it's still also, and I put a little bit more Euclidean regularity to it, it looks like a set of dodecahedrons stuck to each other. Of course, if I put even more Euclidean regularity to it, for this kind of pattern, I get a tetrasoid, something that looks like it's made out of cubes. So there's two limitations to this. I'm not done with the story exactly yet. One of them is that I don't control scale. I can add some Mobius regularity, but some Euclidean regularity, but if I don't, I still get really nice triangles, but some of them are really big, some of them are really small. That's a limitation of conformal transformation. The other big limitation, which I'm going to solve now, is that the energy is really non-convex. The optimization is extremely slow. It can take up to a minute or two when you move some vertex. It's not nice. Which brings me to to the last point of this talk, the last work I also do. How to make this work in, let's call it, a low-dimensional version. Because basically what I'm trying to optimize for is a mesh which is extremely smooth, and if I try to do it with a lot of triangles or polygons, it's a little bit too much. Why am I optimizing for something so smooth with so many elements? The number of vertices is too much for this energy. In fact, I want to do something a little bit more low frequency. For this, we made up something that is actually a level of detail hierarchy. You could optimize for regularity with very few ones, and then subdivide in a way that preserves the regularity. Okay, so for instance, I'm looking at this funny thing. It doesn't look regular, but it is regular. The point here is actually on a sphere, and they are symmetric. So in the new subdivision method I'm going to talk about now, it refines slowly to something very, very regular and spherical around it. How do I do that? When the one-liner that I'm going to talk about is, I invented a subdivision operator that commutes with Mobius transformation. That means you can first subdivide and then do a Mobius transformation, or the other way around, which means it's invariant to Mobius transformation, which means it will create this effect. But let's see how. And therefore, I can do editing. I'm saying, okay, I don't need to optimize on this really, really terribly fine mesh. Okay, I can optimize on the very, very coarse mesh. It's going to take really, really little time because it doesn't have much elements. And then I can subdivide and we'll still keep the nice regularity on it. It's nice. Optimization and subdivision is very small time around. Okay. First of all, a little primer. I'm saying the word subdivide a lot, but it's not obvious, maybe. Subdivision surfaces are surfaces that you refine by entering other elements. The most common one is Catmull-Clark. You just put some element in every face, you connect it by bisection. You don't put the element in the middle of the face, you do some kind of, if you know Bézier stuff or B-spline stuff, it's actually like knot insertion. So you refine the curve by repeated smoothing until it becomes some kind of limit surface. That's how subdivision is done. Now the rules are usually linear, aka it's a multiplication with a matrix, and stationary, which means the matrix is constant. It doesn't depend on the vertices. So to make a subdivision directly from level 0 to level k, you can just multiply all the matrices in advance and then apply them. The problem with linear subdivision is that they really distort a lot of features. For instance, they don't preserve sphericalness at all. Because it's like a B-spline thing, like in knot insertion, they also lose a lot of volume. If you have a feature which is kind of spherical, like the edges of the cubes, they don't preserve them. So that's what we will. They're not good for this purpose. I mean, you could always subdivide, optimize, but you want something a little bit more, with more aptitude to the problem. So, long story short, how do I do that? Using the previous tools I already did, essentially the tangent polygon, I do the following. Given some mesh, I want to optimize it in a way which is Möbius invariant. I know the tangent polygon is Möbius invariant. Okay? So I have a canonical form. I'm going to be using it. So I'm computing a canonical form, computing for every vertex star its canonical form. I'm moving every vertex star to its canonical form, doing the linear subdivision in there, whatever linear subdivision I chose, whatever you want, and then moving it back. So I'm taking linear subdivision, and I'm wrapping it around with, please move to the canonical form in this, and then please move back. By doing this, it's very general. Every linear subdivision I want will have these properties. But let's see a little bit what I mean by saying this. Okay? First of all, the first step. How do I do that exactly? There's still a problem. If I take the original ring, the transformation that brings it to the canonical form is not helpful. Because the transformation is actually like a stereoscopic projection. It takes this vertex to infinity, and then this becomes the tangent polygon. That's not good enough. I wanted something to play with linearly afterwards. So I need to supplement it with another transformation. The one we chose is inversion in its own circle. Why? Because if it's Mobius regular or Willmore, it's already planar, then it will keep this planarity. The result will be that if I take any one ring you want, if it's spherical, then you'll get something planar in the end. If it's regular, you get something regular in the end. That's a guarantee by definition, by construction. Just because the way the tangent polygon is. And now notice this is also local. It's a single, it might be a little bit expensive because it's quaternion, but it's totally local operation in closed form. There's no optimization here. And that's almost basically it. That means that I have a Mobius transformation between this and this, this and this. I subdivided linearly. I put some points in here. Then I take them back using the same transformation backwards. The end. Except not really. Because if you look at it here, I do it for every one ring individually. I still need to blend these points. So for instance, I need to take this curve and blend them. So it required a little bit something extra. I won't talk about it a lot because we don't have much time. But this is a method that does a blending which is Mobius invariant. To be Mobius invariant, you need to preserve cross ratios. So basically, if I computed some new point P from, this is abstractly some one ring, and this is a neighboring one ring, and I want to blend it together, then I'm computing a point P, which is the square root of the original one. Okay, so I'm prescribing the cross ratio for point P, and it's going to be like this. Because I'm using cross ratios, it's Mobius invariant, no matter how I do it. I also need, so by the way, as a side effect, it gave me a method to subdivide curves in a Mobius invariant way. That means if I have a curve that is on a circle, then if I subdivide it, I get a curve that reproduces the same circle. Or if the curve is on a sphere, even. No matter how weird, it gives me a curve on the sphere. But that's aside. This is another operator that helps me blend them if they have the different connectivity, but I won't go into it. The only thing I want to say about this is that it also uses square roots of coarse ratios. So it's still Mobius invariant. But it's not entirely important. I want to get on with it. Okay. So what if it's Mobius invariant? How do you still reproduce all those nice spheres and so? The key element of why I have this reproduction is because linear subdivisions preserve planes. If you have something planar and you subdivide using a linear operator, you get something in the plane. If you have something that is on a line, you still get points on the same line. And also, if you have something that is perfectly regular, well, most linear subdivision operators will preserve this regularity. Try to do Catmull-Clark on a perfect quad mesh, you're getting against another perfect quad mesh. So that means if I had a mesh that was on a sphere, and the transformation took every one ring to the plane, and then when I subdivided it was still in the plane, then when I took it back, it was on the same sphere. So if I have a mesh that is totally on the sphere, by definition, my subdivision will keep being on the same sphere, even if it's extreme. So this doesn't look like much, but all of those points are on the same sphere, just very close to a circle. So the subdivision will reproduce the sphere. All right, so this I can just use for direct editing. I'm taking some kind of pattern, I'm editing only the cage, and then I'm subdividing in place. Okay, and then I'm getting a very, really nice spherical behavior of this, as if I optimized for it after subdivision. So that's very nice. And then one of my targets was to make better optimization for regularity. So instead of taking some core structure, first subdividing, and then doing optimization, which takes forever, like what I showed before, instead I'm doing a coarse optimization. So this is a Mobius regular mesh of that. That didn't take much. And then I'm subdividing the fine result. Okay? The fine result looks almost exactly the same. Yes, since it's only Mobius regular as possible, so it's not exactly the same result. If it were exactly Mobius regular, it would be. But it's almost indistinguishable, and it costs a lot less. Okay? And most of this cost is still the optimization. The subdivision took nothing. So if you make the optimization better, even if it doesn't scale, it still makes the result much nicer. Okay? Let me show one result of editing with it, and then I'm practically done. Yes. By the way, you see it also takes the boundaries to something really circular and nice. So I'm adding in this. This is real time. Okay, the cage. And then I'm getting a very spherical, nice result by doing this. Okay, although the space is very low dimensional of what I'm editing. Yeah, that's enough for this. Right, so that was the technical aspect. Just what I want to do with this in the future. Okay, like any good research avenue, it opened more questions than it actually answered. There are stuff that look like each other, look like previous works with ways we don't entirely understand. For instance, one of them I showed you is this Dupin cycled thing. It's not by chance. So one of them is, it might also appeal to you, this were very geometric stuff, yes, I gotta see. But it would be nice to have other constraints that are also fabrication. For instance, somehow do something that is both Möbius regular and relates to the stress of the object. There's definitely some relation because this regularity relation is also some sort of, let's call it stable. Like the thing I showed before is that topology optimization turns to make these shapes that look like regular, Möbius regular quad meshes. I think it's not by chance. It probably has some kind of thing with the angle preservance and so forth. So this is something I want to explore. Something else I want to explore is what happens in the continuum. Okay, so it's not, I talked about how one circle goes to another circle discretely, and yes, there's subdivision. But the thing about piecewise-affine transformation is that they tell you whatever every point in the triangle goes, and I don't have this. It's very discrete, it's very specific circles go. I want to know if this has like a very finite element way of expression also. So there's something like actual continuous piecewise Möbius. That's very interesting. And that's, yes, of course, on the theoretical part, do all kind of calculus with it. How do the vector fields, the gradients of those transformations look like if you can design by them, and so forth. So thank you very much.